Kia ora. In these first few videos, we're going through some preliminary material you're going to need to study abstract algebra. Last time we looked at equivalence relations, which gave us a more general way of describing what it means for two things to be equivalent. And in this video, we're going to focus on equivalence classes, which basically are what equivalence relations do to a set. They cause it to be split up into a number of pieces. So let's get stuck in. So we're going to illustrate the general idea with our Lego bricks again, but do note that these ideas don't just apply to finite sets like this one, they work for infinite sets too. So here's our set of bricks, and for our equivalence relation this time I'm going to go for the one that says that two bricks are equivalent if they're the same color. So to make what we call an equivalence class, we just pick a brick, let's call it A for example, and then all we have to do is find all of the other bricks that are equivalent to it. So I'd go take my brick, go through them all, and if I find a brick that's equivalent, in this case that's the same color, I collect those ones together. So what I've got here is called the equivalence class of my set S containing my brick, sorry, this one here, wasn't it? My brick A. And you can probably see that I could have chosen any one of these bricks to construct my equivalence class, and I would have got the same set, and we'll prove that in a minute. So in terms of a formal definition, an equivalence class is defined like this. So if tilde is an equivalence relation, so equivalence classes only make sense in the context of having a relation to work with, and then we've got a member A from our set, that's like the brick I picked up before, then the equivalence class of S, the set containing the element A that I picked out, is given by just the set of all things in our bigger set S such that X is equivalent to A. And that's called the equivalence class of S containing A. So maybe let's have a look at an example, just to get away from the Lego bricks for a second. So one example might be if I'm looking at the integers mod 4. So remember our equivalence relation here is two integers are equivalent if they differ by a multiple of 4. So let's build some equivalence classes. So basically we have the definitions is that A is congruent to B mod 4 if A minus B is equal to 4k for some k. Right, so if I wanted to, for example, build the equivalence class of 1, so 1 is an integer, so I'm just looking for all of the integers for which 1 minus that integer gives me a multiple of 4. So if I were to use the definition, it's going to look like the set of all things in my underlying set, which is the integers, such that x is equivalent to 1 mod 4. So I can work that through. So that means it's the set of all x in the integers such that x minus 1 equals 4k for some k in the integers. And so you can see that these are just going to be all the numbers that differ from 1 by a multiple of 4. And so that's going to be, if I were to sort of try and sketch this out, it would be like -7, -3, 1, 3, 7, etc. Okay, so maybe as an exercise you might want to try constructing some other equivalence classes. And it's interesting to see how many different equivalence classes you can actually make in this case. Now, remember I alluded to the fact before that if I've got an equivalence class, like this one here, I could have chosen any one of these three bricks to represent it. So that's kind of a worthwhile enough mathematical statement on its own to do a little proof of. So I'm going to state that as a mathematical lemma. So the way we would say that is basically if we take something from our equivalence class, if I take one of my bricks, then that will also give me the same equivalence class. So mathematically speaking, I can say if B is a member of the equivalence class of S containing A, then actually the equivalence class generated by that is the same as that generated by A. So let's prove this. So basically what we have to do here is we have to show that two sets this one and this one are equal. Now when we want to prove that two sets are equal, the general idea is to show that two sets are equal. We show first that the first set is contained inside the second one, and then we show the other way around. It's a very common pattern that we'll end up using in quite a few proofs throughout the course. When we want to establish that two sets are equal, we'll basically most of the time use this technique. So to show that, let's just write down what we know. So if, first thing, we'll just make a little statement. If B is a member of the equivalence class containing A, that means we know that B is equivalent to A. So we're going to make use of that, so I'll just write it out separately. So I'm going to start by trying to show that the equivalence class containing A is contained within the equivalence class containing B. That means I need to go through this box here and find all of the elements and see if, or show that they're going to be inside the set, the equivalence class containing B. So I'll take an arbitrary one. So I'm going to say let X be an element of the equivalence class containing A. And I want to show that this is also got to automatically be inside the equivalence class containing B. So if X is a member of this, that means we know that X is equivalent to A. And now we have two facts that we can tie together. If you remember the definition of equivalence relations, by transitivity, this means that X is automatically going to be equivalent to B as well. Therefore, by transitivity, X is therefore also equivalent to B. And if X is equivalent to B, that means X is a member of its equivalence class, the equivalence class containing B. So what we've shown is no matter which X we pick from our set equivalence class containing A, it's automatically going to be in the equivalence class containing B also, which means that the equivalence class containing A is a subset of the equivalence class containing B. And then we can say by symmetry, because the argument is exactly the same to do it the other way around, the equivalence class containing B is contained in the equivalence class containing A, and so the two equivalence classes are equal. Okay, so the takeaway from this proof is, well, one of obviously the point about equivalence classes, but also the fact that if we want to prove that two sets are equal, this is a common technique and how the pattern of a proof will often take. Okay, now you might have noticed if you worked through those equivalence classes of the integers mod 4, that you could actually only found 4 examples. So hopefully if you did that, you would have found that the only ones you can get are 1, 2, 3, and 4, or 0. So if you try and make any other equivalence class, you'll actually just get one of these ones back again. So there are only 4. So you might also notice that those equivalence classes, they don't overlap at all, and they cover, between them, they cover all of the integers. And so when we get a situation like that, we call it a partition. So a partition of a set is just a collection of non-empty subsets that when you take them all together, you get the entire set. Okay, it's a little bit awkward wording, but just going back to our Lego bricks for a second, if I were to partition them, basically just means a way of taking up all of the elements of my set and dividing them into subsets that don't overlap. So this would be a partition of my set of Lego bricks into 6 non-overlapping subsets. Okay, so for example, if we're looking at the integers again, just to practice on a infinite set, I could take the even and the odd numbers, and they would be a partition of the integers. There's one of them, and the other one would be the odds, so and they themselves are members of the partition. So that there is a partition of the integers z. Okay, there are two subsets that don't overlap in any way, and between them, if you put them all together, you get all of the integers, so that's what a partition is. Okay, we're now ready to kind of look at the main point of this video, which is that equivalence classes actually automatically form a partition of your set. And we saw that with the Lego bricks. If we took the color equivalence class for this collection of bricks, it automatically makes a partition. Okay, but to actually prove that is a little bit more complicated. So here's the theorem. The theorem says that the equivalence classes of an equivalence relation on S constitute a partition of S. That's the first part. Second part is, conversely, for any partition P of S, there is an equivalence relation whose equivalence classes are the elements of P. Now, it's a lot of words, and it's a lot of sort of jargony words, but basically there are two separate statements here. The first one says the equivalence classes constitute a partition of S. Okay, that's statement number one. And it's actually a completely separate statement to the second half. The second half, the conversely, basically says if I have a partition, I can find an equivalence relation. So it's almost a completely separate problem. So we're going to prove this, but we're going to do the two pieces quite separately. So we're going to start with this one. So this says that the equivalence classes of an equivalence relation constitute a partition. Right, so that's just a fancy way of saying if we've got a relation like colors are equal, then that will automatically split our set up into these equivalence classes, into a partition. So to show that our equivalence classes make a partition, there are two things we need to show. The first thing is that then there are no bricks left out. Okay, there's no bricks that aren't in an equivalence class because we have to cover the entirety of our set. The second thing we need to show is that the equivalence classes don't overlap at all. So if we were to break this down even further, so we need to show number one would be every element is in an equivalence class. And number two, that they don't overlap. Those two things put together will give us the partition. Okay, so let's start with number one. So number one, so I need to go take an arbitrary element of S. So I'm going to take X to be a member of the set. And my goal is to show that it's inside one of the equivalence classes of some sort. So that's actually quite straightforward because all I have to do is build the equivalence class containing itself, and that's all we need. Okay, X is an element of the equivalence class containing it, so every element is in an equivalence class. Okay, that wasn't so bad. Now what about step two? Step two says the equivalence classes don't overlap. Okay, let's just think about how we might show that. So what we're going to do is we're going to take two equivalence classes. Let's just unjumble these bricks back up again. If I'm taking two equivalence classes, as far as I'm aware, the equivalence classes are sort of represented by a single element. So it's like what I'm actually doing is just pulling out two bricks as the representatives, or that's the thing inside the square brackets, and I want to know if the equivalence classes overlap or not. Now if you think in terms of our Lego bricks, if I were to take these two as my representatives, the red and the blue one, then that's what the equivalence classes would be. They wouldn't overlap. That would be great. Another thing that might happen is, for example, I could end up taking these two elements. And if I were to build the equivalence classes, just rope in some more bricks, then actually what I'll get is the same set twice. So what I should expect to see is that if I just take two arbitrary equivalence classes, if there's an overlap between them, then the only way that can really be true is if they're the same set. That's what I should be seeing. So what I'm going to do is I'm going to take two equivalent classes and see what happens. So what we'll do is we'll say let A and B be two equivalence classes. Okay, so as far as we're concerned, they're just represented by two single elements. Now, if they don't overlap, then there's nothing really more to do, because that's what we're trying to show. So we just need to, the case we need to hone in on is the one where there is some kind of overlap between these equivalence classes. So suppose the two overlap, which in set notation means suppose the intersection of those equivalence classes is non-empty. Okay, so you're imagining a picture a bit like this with a Venn diagram. Here would be A, this would be B. Inside their equivalent, this should be the equivalence class containing A, this would be the equivalence class containing B, and we're assuming that they overlap in some way, that there'll be some element in between. Okay, so let's choose ourselves that element. So let's say, because we've decided it's non-empty, we'll say let C be a member of a intersection equivalence class containing B. Okay, so far so good. What does that mean? Well then, if it's a member of both of those things, this means that C is equivalent to A and C is equivalent to B. That's one statement we can make. But in fact, we can do even better than that. Remember that lemma we showed before? I'll just flick back to it really quickly. That lemma said that if an element is a member of an equivalence class, then the two sets are equal. So if I apply that to this problem here, this says that because C is a member of the equivalence class containing A, this means, so even stronger than these statements, by our lemma, actually just in two steps just to not overly rush through. So C is a member of the equivalence class containing A, and hence the two things are equal. And similarly, we also have that the equivalence class of C must also be the equivalence class containing B. And because those two things are equal, they must also be equal to each other, because equals is an equivalence relation, and transitivity applies here as well. So therefore, the equivalence class containing A is equal to the equivalence class containing B. So what have we said? So we've basically shown that if two equivalence classes overlap in any way, if there's an element in common to them, then they're actually just the same equivalence class. There's no difference between them. So the only other possibility is that they don't overlap, which is fine. And so those two facts put together are telling us that we have a partition of our set. Okay, what about the second part of the theorem? Second part says for any partition P of S, there is an equivalence relation whose equivalence classes are the elements of P. Okay, this one's a bit weird. So if we've got a partition, let's just make up a partition of our set of bricks. Let's get rid of these ones, don't need them anymore. Here we go. Not a very interesting partition, but it is a partition. I've split it up into 4 pieces. Then the equivalence relation we want, we just define 2 bricks to be equivalent if they're in the same subset. That's all there is to it. So let's write that down. If P is a partition of it, if P is a partition of S, we're going to define our equivalence relation, because we have to come up with one to prove this. Such that A is equivalent to B if they are in the same subset of P. Okay, so with this partitioning, my equivalence relation is going to say that these 2 bricks are equivalent because they're in the same subset. Also that these two bricks are equivalent because they're in the same subset, etc. Let's move them down a wee bit. Okay, so is that an equivalence relation? Well, let's just work through the properties really quick. So the first one, we have to show that this thing we've defined is an equivalence relation. So that means it has to be reflexive. So we're just asking the question, basically saying, if I take one element twice, is it in the same subset as itself? Yes, and I'll let you actually maybe write these out in full for yourselves. Second one, is it symmetric? This is asking the question, if A and B are in the same subset, is it also true that B and A are in the same subset? Yes, indeed it is. If these two green ones are in the same subset, it's also true that if I switch the order around, it's the same. So that's fine. And then the transitive property is probably the most tricky one, but also not that difficult. If these two bricks are in the same subset, A and B and C are in the same subset, then it follows that A and C must also be in the same subset, so the transitive property is also true here. So give that a tick as well. And maybe as an exercise you could try and write this out slightly more formally. Okay, that's enough for the moment. So hope you enjoyed that, and we'll see you in the next one. Ka kite anō.